Chapter 18, Example 2. An experiment finds 27% of 53 subjects report improvement after using a new medicine. Create a 95% confidence interval for the actual cure rate. So we start by checking the conditions. Since the sample is from an experiment, it is reasonable to assume we have a random sample. It doesn't tell us that, but we can assume it from a properly designed experiment. And we are testing the medication, so the 10% condition does not apply. Our population is the medicine. The experiment would result in 14 patients that showed improvement and 39 that did not. Both at least 10. The conditions are met. I will use the normal model for a 1 proportion Z interval. Okay, so N equals 53, P hat equals 0.27, that's given to us, 27%, and Q hat equals 0.73. Again, the hat, because this is from a sample, it's not the true value. We're not taking a census. So we need to find the standard error. The standard error of P hat equals the square root of P hat times Q hat, so 0.27 times 0.73 over the sample size of 53. And this will equal 0.0610. So we have a normal model, 0.27, 0.061. So let's figure out that margin of error. We want a 95% confidence interval, so our Z star is 1.96. We talked about this in a previous example. It's a little different than 2. The margin of error of P hat equals 1.96 times our standard error of 0.0610, which comes out to be 0.1196. So our 95% confidence interval will be that 0.27 plus or minus 0.1196, which comes out to be 0.1504, 0.3896. I am 95% confident that between 15% and 39% of patients using the medication would show improvement. Now let's just create a 90% confidence interval for the actual cure rate. We already checked the conditions, so we don't have to go through that again. That didn't change. What we needed to do is find a new margin of error. The 90% confidence interval will have a Z star of 1.645. You look that up in the table for 90% and you get right between 1.64 and 1.65. So our margin of error of P hat will equal the Z star 1.645 times the standard error that we already found, 0.0610, which comes out to be 0.1003. So our 90% confidence interval will be 0.27 plus or minus that 0.1003, which gives us an interval of 0.1697, 0.3703. I am 90% confident between 17% and 37% of patients will show improvement when using this medication. So that interval's a little bit smaller than what we had before. What sample size would we need in a follow-up study if we want a margin of error of 5% with 98% confidence? So now we get to do some algebra. Just back to some Algebra 2 stuff. So for a 98% confidence interval, we get a z-star of 2.33. Again, we get that from looking in the table. So the margin of error is 5%. We're just going to plug all this stuff into our formula. 0.05 equals 2.33 times the square root of p hat times q hat, which is 0.27, times 0.73, over n. Now, n is what we don't know. That's the sample size of what we're trying to find, so we're just going to solve. Algebraically, we get rid of that 2.33 in front of the square root. So we'll have 0.05 divided by 2.33, and this will equal the square root of 0.27 times 0.73 over n. Now you can go ahead and multiply all that stuff earlier. So we get 0.0215, which equals the square root of 0.27 times 0.73. And again, if you multiply that numerator earlier, that's perfectly fine. And so that's all over n still. Now we want to square both sides. That's how you get rid of a square root. So we get 0.0215 squared is going to equal that fraction, 0.27 times 0.73 over n. And we get 0.00046 equals 0.27 times 0.73 over n. Now we're going to move some stuff around, move that n around. 0.00046n equals 0.1971. I went ahead and multiplied that 0.27 and 0.73 finally. Now we've got to divide by the 0.00046, so I get n equals 0.1971 divided by 0.00046, which gives us 428.5. We would need to run the experiment with at least 429 people receiving the medication in order to have a margin of error of 5% with 98% confidence.